Hello everyone, I am Dr. Preeti. Here I will be discussing oscillator topic from the subject analog circuits, that is KEC 402. The oscillators that uses positive feedback. In the previous discussion, previous video, I have discussed about the feedbacks. There we have seen that what is a negative feedback and a positive feedback. So here with the oscillator circuits, we will be having the positive feedback in the circuits. So the first diagram here is showing an amplifier and the second one is for oscillators. So here with the amplifiers we can see that the signal, here we have the input signal and the output signal that we are getting at the output, and that basic required DC power input is present here. But with the oscillator circuit, we can see that here we have DC power input that is required to operate the circuit and the signal output. Here we do not have any external input to this oscillator circuit. This oscillator circuit oscillates and it amplifies the signal that is generated within the circuit. We have different classifications of the oscillators, electronic oscillators, that may be broadly divided into two groups. One is your sinusoidal oscillator, second one is your non-sinusoidal oscillator. Sinusoidal oscillator is also called as harmonic oscillator that produces an output having the sine waveform. Non-sinusoidal oscillator or the relaxation oscillator, they produce an output which has a square, rectangular or sawtooth form of or the pulse shape. Sinusoidal oscillator can be further classified into tuned circuit or LC feedback oscillator. For example, Heartlay oscillator, Colpitts and Clap oscillator. Then we have RC phase shift oscillators such as Wien bridge oscillators. Negative resistance oscillators such as tunnel diode oscillators and crystal oscillators such as Pierce oscillator. So we will discuss all these oscillators one by one. Oscillators are used to generate signals. Used as a local oscillator to transform the RF signal to IF signal in a receiver. It is used to generate RF carrier in the transmitter. We can use to generate clock in the digital systems. We can use it as a sweep circuit in TV sets and CROs. The oscillations in the oscillatory circuit can be a damped oscillation, it can be an undamped oscillation. So sinusoidal oscillations produced by the oscillators may be a damped oscillation and an undamped oscillation. Here the oscillation that is shown on the screen is the damped oscillation. Damped oscillation is the oscillation where the amplitude of the waveform is decreasing with the time. So here we can see the amplitude is initially more and it is reducing with the time. So these type of oscillations are the damped oscillations. Undamped oscillation, here the magnitude of the signal does not decay with time. It is having a constant magnitude with the time. So how the oscillations are being produced. So this diagram is showing an oscillatory circuit. Here we have a capacitor and an inductor and switch S. When the capacitor is fully charged, the plate B, that is positive, and plate A is negative. So positive charge move from B to A, and when we close the switch. So here the negative charges are in majority, so it will move and it will contribute to the flow of current. That will generate field in the inductance, and after some time the plate B becomes more negative as compared to plate A. Then again the negative charge starts flowing from B to A, and the direction of field here is just reverse. In that way the oscillatory motion is conducted in the oscillator circuits. These oscillations of a capacitor discharge are damped because energy is dissipated away gradually, so that their amplitude becomes zero after some time. There are two reasons for loss of the energy. Some energy is lost in the form of heat produced in the resistance of the coil and connecting wires, and some energy is lost in the form of electromagnetic waves that are radiated out from the circuit through which an oscillatory current is passing. Frequency of oscillatory current. The frequency of time period of oscillatory current depends on two factors, that is capacitance of the capacitor and self-inductance of the coil. That is frequency that we can write here as F is equal to 1 upon 2 pi under root LC. That is 159 divided by under root LC kilohertz. Here L is the self-inductance in microhenry, C is the capacitance in microfarad. Frequency stability of an oscillator. So the ability of an oscillator to maintain a constant frequency of oscillation is called its frequency stability, and the factors that affects the frequency stability are operating point of the active device, inter-element capacitances, power supply, temperature variations, output load, mechanical vibrations. The Q point of the active device, that is the transistor, is chosen as to confine the circuit operations on the linear portion of its characteristics. Operations on non-linear portion varies the parameter of the transistor, which in turn affects the frequency stability of the oscillator. If we talk about power supply, so changes in the DC operating voltage applied to the active device shift the oscillator frequency, and this problem can be avoided by using regulated power supplies. Output load. A change in the output load may cause a change in the Q factor of the LC tuned circuit, thereby affecting the oscillator output frequency. Mechanical vibrations. Since such vibration change the value of circuit elements, they result in the changes of the oscillator frequency. This instability factor can be eliminated by isolating the oscillator from the source of the mechanical vibrations. The essentials of any feedback LC oscillator. So these are the components that are essentially required to design any feedback LC oscillator. Here we have resonant circuit that is made up of L and C. The output that here gets amplified through the amplifier circuit, and some part of it is fed back to the through this feedback network, and we are measuring output here. That is your output that we are getting from this LC oscillations. The essential condition for maintaining oscillations and for finding the value of frequency is that A beta should be equal to 1 plus J0, and the angle should be phi or 180 degree. It means that the feedback factor for the loop gain should be 1 and the net phase shift around the loop should be 0 or an integral multiple of 360 degree. In other words, we can say that the feedback should be a positive feedback. So the condition from Parkinson's criteria for maintaining a steady level of the oscillations at a specified frequency, the majority of the oscillators used in the radio receivers and the transmitters use tuned circuit with the positive feedback. Variations in the oscillator circuits are due to the different ways by which the feedback is applied to the system. So some basic circuits that we have is tune based oscillators, Heartlay oscillator, Colpitt's oscillators and clap oscillator. With Heartlay oscillator, the feedback is supplied inductively. In the Colpitt's oscillator, the feedback is supplied through the capacitive effect. With the clap oscillators, we have a slight modifications of the previous one, that is Colpitt's oscillator. This is the circuit diagram for Heartlay oscillator. This Heartlay oscillator is designed using bipolar junction transistor. We can also design this oscillator using field effect transistor. Here RFC is the coil that is for the inductor that is connected here. R1 and R2 are the biasing resistances connected at the base terminal of this transistor. L1, L2 coil and the capacitance C, this is responsible for creating oscillations in the circuit. Here in the figure B, the AC equivalent circuit of this oscillator is shown. With the AC equivalent circuit, the capacitances are not shown here. Only the BJT is there and its oscillatory circuit. So here the frequency of this oscillator is defined as 1 upon 2 pi under root LC. The value of L that we can calculate as L1 plus L2 plus 2M, that is mutual inductance between the two coils. Colpitt's oscillator. So here if we see the previous one, here we have two inductive coils L1 and L2. With the Colpitt's oscillator, that is, you can say, an interchange between the inductor and the capacitor. Here we have two capacitances C1 and C2 and a inductor L with a series with a capacitor C3. Again here we have a BJT, bipolar junction transistor. Here the R1 and R2 are the biasing resistances and C5 that we use at the one end of this coil. We have a switch at the top through which we can connect the supply to this circuit. AV, that is defined as 1 upon C1 by C2, that we can simply write as C2 by C1. So the tank circuit consists of two capacitors C1 and C2 and a fixed coil. The frequency of oscillation that does not depend upon the mutual inductance, we can write it as 1 upon 2 pi under root LC. Here we have two capacitances. So this C is the equivalent capacitance that comes from the equivalent capacitance of the two capacitances C1 and C2, that we can calculate as C1 C2 upon C1 plus C2. Transistor itself produces a phase shift of 180 degree and another phase shift of 180 degrees provided by the capacitive feedback. So it gives a total phase shift of 360 degree between the emitter base and the collector base circuits. Clap oscillator. Here the two capacitances C1 and C2 are there with the coil L and C3. Next is the phase shift oscillators that based upon the principle of phase shift. Tuned circuits are not an essential requirement for the oscillation. We can have oscillations without having the tuned circuit. So the essential requirement is that there should be a 180-degree phase shift around the feedback network and the loop gain should be greater than unity. The 180-degree phase shift in the feedback signal can be achieved by using a suitable RC network, and the total phase shift required in 360 degree. So the balance of 180 degree is provided by the active device of the amplifier. So we have different oscillator circuits that work upon this phase shift principle. The first one is the RC phase shift oscillator. This is the circuit diagram of RC phase shift oscillator that is designed using bipolar junction transistor. Here resistance R5 and R3 are the biasing resistance, and here we have network of capacitance and resistance. At the output side we are having resistance RC. In the emitter branch, one resistance R4 is connected through this bypass capacitor C4. C5 is the coupling capacitance that is connected at the output side of this phase shift RC phase shift oscillator. So here we can see that there is three combination of resistance and capacitances. So with these three, what we can see is that with one combination of R and C, we get a phase shift of 60 degree. So here we are having three such combinations of resistance and capacitance. One combination will provide a phase shift of 60 degree. So here we are having three. So this will provide us a phase shift of 180 degree through this combination of resistance and capacitances. Another 180 degree phase shift will be provided by the active device. So total here we will be getting 180 degree plus 180 degree, and total phase shift that we obtain from this RC phase shift oscillator is 360 degree. So the frequency of oscillations for this 3-section RC oscillator, when the 3 R and C components are equal, can be given as 1/2 pi under root 6 RC hertz. If we simplify these numerical value, then we get it as 0.065 divided by RC. The another phase shift oscillator, that is Wien bridge oscillator, that works upon the principle of phase shifting through the RC network, and another phase shift that is provided by the active device. So here we have this bridge network, that is A, B, C and D. So due to this bridge it is called as bridge, and Wien is the name of the scientist who discovered this, who designed this Wien bridge oscillator. So here we can see that we have one parallel combination of R2 and C2, and another one is R1 and C1. So with this combination of R and C and this total phase shift that is provided by this phase shift network and including the transistor, we get a complete phase shift of 360 degree. That is basic requirement for any oscillator circuits. Bridge circuit principle, that it is found that Wien bridge would become balanced at the signal frequency for which phase shift of 0 degree or 360 degree. So the balanced conditions are R4 upon R3 should be equal to R1 by R2 plus C2 by C1. and the frequency omega naught can be defined as 1 upon under root R1 C1 R2 C2. Further, we can write it as 1 upon 2 pi, that frequency, that is 1 upon 2 pi times omega. So that will give us 1 upon 2 pi R1 C1 R2 C2. And if we have this condition that R1 and R2 are equal and it is represented by a resistance R, and capacitance C1 and C2, that is represented by an equal capacitance of C. So frequency can be written as 1 upon 2 pi RC, and R4 by R3 is equal to 2. We have non-sinusoidal oscillators that gives us an output that is not in the form of sinusoid. That can be a sawtooth generator, blocking oscillator, and a multi-vibrator. Thank you.